Okay, in this video I'm going to try and introduce you to inner products, which are kind of going to lay the foundation for what we're trying to do in chapter 11. The inner product is a new way to multiply two functions, and so it's not exactly multiplying two functions because you would expect a function times a function to be another function. What it's actually going to be is a new way of multiplying where the answer ends up being a number, and so we're actually going to use a definite integral on some domain. And so the definite integral of two functions is going to be a number. And the reason this is important is that there's another product we've seen before where it was a product of two weird things where the answer ended up being a number, and that was the dot product. And there's a lot of things you can do with the dot product, like find the length of a vector or find the projection of a vector. And so we'd like to do something similar with functions. And so the way we do that is using this thing called an inner product, which ends up just being the definite integral of the two multiplied together. So this might look kind of similar to a convolution that we've talked about before. It's not quite the same, though. It's something new. The convolution was a new function, whereas this is going to spit out a constant. Okay, so if we're talking about two functions, they're called orthogonal. And so if you think back to vectors, orthogonal and perpendicular both kind of mean the same thing. They mean they are at a right angle. For functions, they're not really going to be at a right angle, but this is going to be the equivalent for functions. Basically, it means we're going to be able to do the same things that we could do for vectors like projections and such, if this is our equivalent of perpendicular. Okay, so anyway, two functions are orthogonal if the inner product is 0. And I should have mentioned the inner product has this funky notation just to point out this isn't the normal product. So we just put the two side by side in parentheses to say, okay, this is the new product. Okay, if we have multiple functions, so I'm using the Greek letter phi, phi1, phi2, dot, dot, dot. A set of functions, there might be 2 or 3, or there might be infinitely many of them. They're going to be, the set will be orthogonal if every pair of the functions are orthogonal, or every pair of the functions has the inner product is equal to 0. So we don't necessarily need to have phi1 with phi1 be orthogonal, or have the inner product be 0, but phi1 with phi2, and phi1 with phi3, and phi2 with phi3, all those should be 0. Okay, which then leads you to the obvious question, which is why? Why are we doing this? What are we trying to get out of this? What's the point? And in the previous chapter, in chapter 6, we looked at power series solutions of a differential equation, which is a constant plus a constant times x to the first plus constant x squared plus constant x cubed. What we would like to do is the same exact thing, but with other functions, any old function. Not any old function, but certain particular functions. And so basically we're going to try and do the same kinds of things that we did in chapter 6, plugging in a series to a differential equation and solving for the constants. Only it turns out life is a lot easier if we're allowed to pick what the functions are. So I'm going to make an assumption here. So I'm going to show you why exactly this isn't as complicated as simple powers of x. As far as writing things down, yeah, simple powers of x are simpler than like if these were, I don't know, a square root of x, a sine of x, an arctangent of x, or some weird functions. But if these functions happen to be orthogonal, some cool things are going to happen. So what I'm going to do is I'm going to take the inner product, this new thing we defined up above, of phi 0 with both sides of the equation. So phi 0 comma f. And on the right side, it'll be phi 0 comma everything that's already written down. Okay, so hopefully this makes sense. If f is equal to this thing, phi 0 inner product with f should be the same as phi 0 inner product with whatever this thing is. But the nice thing is we're defining our inner product in terms of a definite integral. And the definite integral, like sums, we can split up a sum of integrals into integral of sums. We can also split up constants times an integral. So using some theorems about integrals, I should be able to split this up into the constant coming up front and phi 0 acting on phi 0. And when I say acting on, I really mean an inner product. And then C1 and phi 0 inner product with phi 1. And then C2 phi 0 acting on phi 2. Plus ... as many as there are going to be, which probably there's going to be infinitely many if this is playing the role of a series. There's going to be infinitely many functions, phi's. Okay, well that looks like a giant mess. But if these functions, the phi's, are orthogonal, the whole point of orthogonal was that if you have two different functions, their inner product is going to be 0, which means that this guy is 0 and this guy is 0. And that's making an assumption if the phi's are an orthogonal set. And so that means that really the whole equation boils down to this thing. And so if I needed to solve for the constants, instead of having to actually plug into a whole differential equation nonsense, if I just want to know the particular constants, it's just going to be an algebraic operation. I just have to do a inner product of phi 0 with f and an inner product of phi 0 with phi 0. And notice that both of these are just definite integrals. And so we're not really scared by doing definite integrals. We could do a Riemann sum even if it was a really complicated function. And there's nothing special about phi 0. We could have done the same thing with phi 1. So replace this 0 with a 1. And then we'd get a formula for C1 and replace this 0 with 2, and we get a formula for C2. And so writing a function as kind of the orthogonal function equivalent of a power series ends up being not too terrible because you're starting with an orthogonal set. A lot of the constants are going to drop out and turn into zeros.